Okay, today we're discussing the mean value theorem. And of course, in mathematics, when you hear the word mean, you think average. The mean value theorem does relate to averages. Let's take a look at the mean value theorem. Once again, let's try a new marker. The mean value theorem consists of two hypotheses and a conclusion. And let's draw a picture of what we're dealing with here. We're dealing with a closed interval from x equals a to x equals b. And on that interval, a function that is continuous throughout the closed interval, that is at the endpoints as well, and differentiable at least through the open interval. Okay, so there's our function, and here are our y values for the endpoints, f of a and f of b. The hypotheses, the conditions that must be true in order for the mean value theorem to apply. One, as I said, f must be continuous on a closed interval. It must be differentiable on at least the open interval throughout the interior. There cannot be any sharp corners, there cannot be any discontinuities. If those are present, then the mean value theorem does not apply. Well, the mean value theorem says that if these hypotheses, if these conditions are met, then we have a conclusion. And our conclusion in the mean value theorem is, if those are met, then there must be at least one x, which we'll call c, such that f prime of c, that is the slope of the tangent line, the derivative at x equals c, equals the slope of the secant line between the endpoints, okay? And that's where the average, the mean, comes in, because the slope of the secant line connecting the endpoints represents the average rate of change of the function y equals f of x over the entire interval AB. And we're saying that given a continuous and differentiable function over that interval, there must be at least, and again, when we say at least, there could be more than one, must be at least one value of x between a and b, and I should have written that, 1x equals c, and we'll just add that right now into our conclusion, where c is between a and b, such that the slope of the tangent line, the instantaneous rate of change, and we can see that there are at least two here, all right about here, the slope of the tangent line here, and the slope of the tangent line here equal the slope of the secant line connecting the endpoints. That is, the instantaneous rate of change at some point equals the average rate of change over the whole interval. If we wanted, let me label these hypotheses. If those are true, that must be true. To give a real-world example of the mean value theorem, think about taking a trip in a car. All right? Suppose that you have to drive 20 miles, and it takes you a half an hour. Well, that means that your average speed for the trip is 40 miles per hour. Now, since position and speed are continuous and differentiable functions, you cannot go from one speed to a much faster speed without going through all of the speeds in between. Then there must be some point at which you are traveling at exactly 40 miles per hour. You cannot average 40 miles per hour if you're always traveling slower or always traveling faster. There must be some point or points during the trip where you are traveling at exactly 40 miles per hour. Okay? That's just a real-world example of the mean value theorem. So that's the theorem. Now, what kind of problems might you be presented with in the mean value theorem? Well, let's take an example. A typical problem might say something like this. Given a function, and we'll use the function f of x equals the square root of x minus 1 over a specific interval, and we'll use the interval 1 to 3. Now, that function is continuous over the interval 1 to 3. It's differentiable in between 1 and 3. So it meets the conditions, the things that must be true in order for the mean value theorem to apply. Right? Given that function over that interval, find the value of c, that is x equals c, that satisfies the equation in the conclusion of the mean value theorem. And again, that equation is that f prime of c must equal f of b minus f of a over b minus a. All right? Knowing that that is the equation in the conclusion tells you what you must find. You must find the right side, the slope of the secant line connecting the endpoints. Well, in this case, that would be f of 3 minus f of 1 over 3 minus 1. So here, f of 3 would be the square root of 2. F of 1 would be 0 over 3 minus 1 is 2. So we have the square root of 2 over 2. That is the slope of the secant line connecting the endpoints of the interval, of the function on the interval. Okay. Now, we need f prime of x. And we'll solve for c. Well, f prime of x is 1 over 2 times the square root of x minus 1. We need that to equal that. And we'll solve for the x value, which will be our c. So, if 1 over 2 times the square root of x minus 1 equals the square root of 2 over 2. Well, one thing that we can do right away is multiply both sides by 2, and that will eliminate the 2's here. Now we can multiply through by the square root of x minus 1, and we'll have 1 equals the square root of square root of 2 times the square root of x minus 1 is the square root of 2x minus 2. If we square both sides, we get 2x minus 2 equals 1. So 2x equals 3. And our answer, x equals 3/2. Three halves, is it in the interval? Yes, it is. Does the value of the derivative at x equals 3/2 equal that? Well, it certainly should, since that is how we arrived at that number, but we could test it to make sure that we didn't make an error here. So let's do that. Let's test that. Using x equals 3/2, 1 over 2 times the square root of 3/2 minus 1. Well, that would give us 1 over 2 times the square root of 1/2. The square root of 1/2 is 1 over the square root of 2. Two over the square root of 2 is the square root of 2. And if you multiply this by the square root of 2 over the square root of 2, you get the square root of 2 over 2. So yes, when x equals 3/2, the value of the derivative is the same as the slope of the secant line connecting the endpoints. All right, now there is one special case of the mean value theorem that gets its own name for some inexplicable reason. That special case is Rowley's theorem. And Rowley's theorem starts with the same hypotheses as the mean value theorem. 1, f continuous on closed interval. 2, f differentiable on the open interval. But then it adds a third hypothesis. That is, f of A equals f of B. In other words, if we set up our diagram, whatever happens in the middle here okay, well, the conclusion then is this. As you might expect, clearly, if f of A equals f of B, the slope of the secant line connecting the endpoints is 0. It's a horizontal line. So the conclusion for Rowley's theorem is there is at least one x equals c, where c is between A and B, such that f prime of c equals 0. Because 0 is the f of B minus f of A over B minus A. The problems that you might see on a homework assignment for Rowley's theorem are perhaps a little more challenging than a standard just mean value theorem problem, and a little more fun perhaps because they force us to think. And thinking is always more fun than just mechanics. So let's do one of those problems. very quickly. Let's take the function f of x equals x cubed plus 3x plus 1. And the problem says, show that this function has exactly one real root. That is, one real value of x such that y equals 0. Okay? How does Rolle's theorem enable us to prove that? Well, we have to combine it with another theorem, the intermediate value theorem. Okay? Because we have to actually prove two things. We have to prove, one, that it has a root, and then two, that it doesn't have another root. Well, it's easy enough to prove that it has a root by the intermediate value theorem. Since the function is continuous everywhere, if we can find one value of x where y is negative and one value of x where y is positive, we will have shown that there is a root. All right? F of negative 1 is negative 1 plus negative 3 is negative 4 plus 1 is negative 3. F of 0 equals 1. Since the function goes from negative to positive, and it is continuous, there must be some value of x between x equals negative 1 and x equals 0, where y equals 0. There is a root. Just schematically, we can say at negative 1, at 0, we have here negative 3, we have here positive 1. There must be some place in here where y equals 0. Now, how do we prove that there is not another place where y equals 0? Well, very simply, this function is continuous and differentiable everywhere. Rolle's theorem says, right, that if there is another place where y equals 0, there would have to be some place where the derivative equals 0, because this function would have to turn around. Well, let's take a look at the derivative of this function. The derivative of this function, f prime of x, is 3x squared plus 3. If there is another root somewhere, this function would have to turn around again. So there would have to be some place where the derivative equals 0. Where does 3x squared plus 3 equal 0? If you said 3x squared plus 3 equal to 0, 3x squared would have to equal negative 3, x squared would have to equal negative 1. In the real number system, there is no value of x such that x squared equals negative 1. There is no critical number to this function. In fact, 3x squared plus 3 for any real number x is positive. This function is always increasing. Always increasing. There cannot be a second root. So using the intermediate value theorem, we can prove that there is one root. Using the opposite of Rolle's theorem, we can say there can't be a second root. And that's that.